Now, you might have heard me refer to vector functions in the previous videos in terms of motion, okay? And that's a quite a suitable analogy, since if we let t actually represent time and the components of our vector function be the x component in space, like real space, and the y component be the y value of position, and z be the z value of the position, then we actually get this position vector, and it's a vector function. Okay. The important part is that t represents time, and uh, this actually is the position in real space. Okay. So if we have that vector function uh, representing position, taking the derivative of the position vector gives us the velocity. Okay? And so here you have the velocity vector written out if the position vector is given here. Notice we're just taking the derivative of each component with respect to time. I can say now with respect to time because we are dealing with motion. The acceleration is the derivative of the velocity with respect to time. And since the velocity is the derivative of position, the acceleration is the second derivative of position. Moreover, the speed, something else that's quite relevant when we're talking about motion, is the magnitude of the velocity. So speed is the magnitude of the velocity, which then is the magnitude of the derivative of the position vector. And it could be written out in this way. Notice that the speed is not a vector. It is a scalar. It's a scalar quantity. So let's take a look at an example. Here we have a particle that has the velocity given by this vector function that you see here. And the motion is running from time t equals 0 to time t equals 1. And we want to find the speed of this motion, the acceleration of this motion, and the position of this motion. And you can't determine the position vector uniquely if you're only given the velocity. I mean, someone could tell you they're going 5 meters per second due east. That's not going to give you their entire path. Now, if they tell you that I've been going 5 meters per second due east and I started an hour ago at this particular gas station, then you can map out their position uniquely. So we're also given an initial position. The initial position here is 1, 0, 0. So they were along the x-axis. Okay. Okay, so first we want to find, this is a typo, the speed. Okay. We would like to find the speed, and the speed is what? The magnitude of the velocity. So the magnitude of the velocity, you just take each component, square it, and add them together. Okay, so we get that term here. Simplifying in here, I just write 1 half to the power of half instead of that square root, since it's just easier to write. You could then, after squaring, and of course the squaring gets rid of that minus sign. Nothing irritates a professor more than someone squaring a minus sign and getting another minus sign. So you shouldn't have minus signs in there once you square. You'll get 4 pi squared, and you could factor out the 4 pi squared, and you're left with this sine squared 2 pi t and cosine squared 2 pi t. They have the same function inside. The sine and cosine have the same function inside. So you could add the square of them to get 1. So since sine squared plus cosine squared is 1 when they have the same argument. And you get this speed. Now, notice something about this. It's constant, okay? Despite the velocity changing in time, the speed is actually constant, and it's just a good old-fashioned number since speed is a scalar. Now, what about the acceleration? Well, acceleration is the derivative of the velocity. So let's take the derivative then of the velocity function. And we do that by just taking the derivative of each component. And what's the derivative of sine 2 pi t? Well, it's going to be 2 pi times 2 pi due to the chain rule, cosine 2 pi t. So that's what you're seeing here. Likewise, taking the derivative of that second component gives you this. And the derivative of 1 is just 0. So our acceleration vector is that vector that you see here. Now, whereas the acceleration was the derivative of the velocity, position is the integral of the velocity. Since the derivative of the position is the velocity, then to get the position, we have to actually get the antiderivative of the velocity, which means the antiderivative of the derivative of position. Okay, so so we take an integral of the velocity to get position. And how do we integrate in an indefinite way? Well, we just integrate each of the components. This here is the component, the x component of the velocity, the y component of the velocity, and the z component is just 1. Integrating in an indefinite way, we get this. Please don't forget the constants. That's extremely important. And you wouldn't be able to finish this problem if you didn't include the constants. So what you see here, okay, in that box, is a position that's consistent. It's a position function that's consistent with the velocity. So for any constants that we fill in, then the derivative of this boxed term here will give us the velocity that we were given in the problem. Okay, so this is consistent with the velocity that we have. Now, we have an extra condition telling us that initially we were here. Okay, we were at 1, 0, 0. And because we have an initial position, we can actually determine the position uniquely. So it's not just, so we could get rid of these constants which allow for ambiguity. No, we actually have an initial position. Our initial position given in the problem is the left-hand side. That's the left-hand side that you see there. That's given. And on the right-hand side, what are we doing to get the right-hand side? We're plugging in 0 into our function that we got through taking an indefinite integral. So we're taking 0 and plugging it into all of these different locations. So we'll have the r of 0 on the right-hand side is 1 plus c1, c2, and then 0 plus c3 there. And now we have to match both sides. So c1 plus 1 equal to 1 implies that c1 is equal to 0. And, c2 is equal to 0 and c3 is equal to 0. Here, if you coincidentally left out the constants, you'd still get the right answer. But that's just a coincidence because it happened to be that the constant vector should be 0 in order to match this initial condition. You can't take that for granted, though, in general. So filling in that constant vector with the constants that we found of 0, we get this position vector, okay? So this position vector has 1, a velocity function that looks like this, and 2 has an initial position of 1, 0, 0. And if you try to plot the trace, you start out here along the x-axis and you move up and along until you make it back to the x-axis at z equals 1. And I plotted for you a few of the vectors. So this is the initial vector, t equals 0, t equals 1/2. We are pointing along the minus x direction at t equals 1/2. And we're halfway up to our final value of z equals 1. And at 1, we reach this green vector there. Also, please note, I just plotted this for t equals 1/4. The velocity is tangential, pointing slightly up because we're moving in the to higher altitude, and the acceleration is always pointing towards the z-axis. Actually, here you could see that by this vector here. So the z component is 0, and it actually points always towards the z-axis. Another thing to note, I mean, sometimes it's extremely common when you plot, something circular to, complete one whole cycle in 2 pi. Here we complete one whole cycle around the z-axis after 1 second. And we obtained that by having the 2 pi in there. So it's not really necessary to always complete a cycle in 2 pi. That's only true if you use the parameter of angle inside your cosine and sine. Here we just let the time run from 0 to 1, and we still made it around the circle. Now what you're seeing here is a different motion, but looks pretty similarly and is just as enlightening. So we'll take a look at it. Okay, this is for a different problem. This, you could see that the vector function given here is has an x component 250 cosine t. And in fact, this does loop around once in 2 pi seconds. So we could vary this t as t goes on. This does a spiral, which is similar to our motion that we had in the example we looked at. But I want you to pay attention to the velocity that you just see here. That's r prime. That's the velocity. And look how it's always tangential to the curve as you move along. It's always pointing in the direction of motion, right? Velocity is the change of position over change in time, so it should point in the change of position, so it should be tangential. And the acceleration is the derivative of the velocity, and it's pointing radially inward towards the z-axis. Not radially inward, but towards the z-axis is a better way to put it. And this makes sense. So if you look at it from above, this is how it looks, because the velocity in the z component stays constant. Okay, the velocity is 100 in the z component. So this motion is rising a rate of 100, say meters per second or feet per second. And so we don't get a change in velocity along the z-axis. We only get a change in velocity along the x and y, okay, in the x and y directions, and the speed is actually constant. Just because the speed is constant doesn't mean that you don't have an acceleration. You could see our green vector is the acceleration. We do have an acceleration. Now think about why that is. How could the speed be constant, but you still have an acceleration? How? How could that be the case? Okay, because the acceleration is not the derivative of speed. The acceleration is the derivative of velocity, and velocity has magnitude and direction. Okay, so if the direction of your velocity changes, you still get an acceleration even if the magnitude stays the same. And that's what we're seeing right here in this problem.